multiple qubits. That's where it gets interesting, because the block sphere is not enough, or at least not the classical representation of a block sphere, to represent two qubit states. While a single qubit gate possesses some counterintuitive features, such as the ability to be in more than one state at a given time. If we all had in a quantum computer were single qubit gates, then we would have a device with computational power that would be dwarfed by even a calculator. The true power of quantum computing only becomes visible as we increase the number of qubits. That's true. The power arises in part because the dimension of the vector space in which quantum state vectors grows exponentially with the number of qubits. A single qubit can be trivially modeled, but 50 qubit quantum computer pushes the limits of existing supercomputers. And I think I've read recently that IBM has simulated a 50 something qubit quantum computer recently, doing some tricks in the way of what other states allowed to be part of the simulation. And it has taken an entire supercomputer to actually do that. Anyway, let's go ahead. Representing two qubits. So the main difference between 1 and 2 qubit states is that 2 qubit states are 4-dimensional rather than 2-dimensional, and that's important. So I think that's important, because the computational basis for 2 qubit states is formed by the tensor product of 1 qubit state. So if you've got 0, 0, right, that's how you represent 0, 0. So that here, it's not, and then 0, 1 is that, and 1, 0. So you don't really, the thing here is you can build up some intuition easily, because you don't, or the way I do this at least is, you don't have to do the tensor product, because you can just imagine that if those are your 4 dimensions, the first one is 0, 0, this is 0, the second one is 0, 1, the third one is 1, 0, and the fourth one is 1, 1. So that's intuitively how I would just understand that. Then a similar rule applies, right? So all the probabilities, all those coefficients, norm squared, must sum up to 1. Yeah, and basically that's what you do. So tensor product, not that well can always take. Okay, so note that while we can always take the tensor product of two single qubit states to form a 2 qubit state, not all 2 qubit quantum states can be written as the tensor product of 2 single qubit states. That's also important. For example, there's no states like alpha, beta, and then however those things are called, that their tensor product is this and this. Yeah, that's so if you have that state, there's no way you can decompose that into 2 separate states. And this is what's called entanglement. So this means that as a system, you can understand that, but you can't separate that. So they are said to be entangled. It can be thought of a tensor product. I mean, you can separate them, but you cannot just think of them as the definition tells you should. The information is stored non-locally in the correlations between the 2 states. So, and this is another important part that I want to explore long term. Short term. That says you can store information in the correlation between the 2 states. So it's non-locally. This means that each of the separate qubits doesn't necessarily encode all the information. To understand everything, you need to take a look at the system at the entire system at once. Measuring 2 qubit states is very similar to single qubit measurements. Measuring the state, it yields 0, 0 with that probability, 0, 1 with that probability, 1, 0 with that probability. That all makes sense, right? And that's easy to understand so far. I mean, even if you don't, without really getting into detail of what's happening behind the scenes. But from a logical perspective, you get that way of representing states, and when you measure, you will get one of the 4 states with a given probability. it's also possible to measure just one qubit of a 2-qubit quantum states. In cases where you measure only one qubit, the impact of measurement is subtly different because the entire state is not collapsed. Rather, it is collapsed to only a subsystem. In other words, in such cases, measuring only one qubit only collapses one of the subsystems, but not all of them. To see this, consider measuring the first qubit of the following state, which is formed by applying the Hadamard transform on 2 qubits initially set to the 0 state. So this is 0, 0, and there's a Hadamard to each of them applied. So basically what's happening here is you have this first portion is the Hadamard gate, and this is basically your state, which is 0, 0, as we said, 0, 0. So but I don't understand. Outcome equals 0, outcome equals 1. Both outcomes have 50% probability of occurring. The outcome being 50% probability for both can be intuited from the fact that the initial quantum state vector is invariant under swapping 0 or 1 on the first qubit. I'm not so sure I understand that. The outcome being 50% probability for both, for these and these, from the fact that the initial quantum state vector is invariant under swapping 0 with 1 on the first qubit. So, I mean, this here means that there's equal probabilities of getting any of the fourth of the 4 states, 0, 0, 0, 1, 1, 0, 1, 1. But I don't really understand what they mean by that. Okay. Measuring the first qubit. So what they're trying to say is, what if we measure the first qubit? I get it. So we're basically saying if you measure the first qubit and it's 0, then you end up with the following. So, okay, then you know what this means is if you measure the first qubit only, that is already transforming the possible outcomes of whatever of the system, right? So if you measure the first qubit to be 0, then your probabilities, or then your state becomes this, not this. So basically, because you know it's a 0, then you know that you can only get either 0, 0 or 0, 1, right? So 0 being the first, so the sort of the leftmost, I assume. While if you measure 1, then the only probable solutions that you have, or the only possible outcomes that you have at the end of the day are 1. That's interesting. I had gone through those basic concepts, but I never had taken a look at them from that perspective. So that's an interesting thing. So you see, so this is just mind blowing, because here we're not talking. This is way different from classical computing, not in just that, because I first thought it's just the same, but with probabilities, right? So instead of zeros and ones, you have like 20% chances of 0, 80% chances of 1, whatever. But it really is not this way. A measurement, the way you measure the state really affects the information that is let's put it this way, it really affects the certainty and uncertainty of the information you have. And I don't really know what you can do with that yet, but that's big. You know, like if you measure the first one and you have 0, then you're basically, by measuring, you're affecting the information you have in your state. That's badass, man. blah blah blah. I'm skipping the mathematical rules. I guess maybe I shouldn't be doing that, but it's just too time consuming, and I'm gonna trust the mathematicians behind that, physicists, whatever. So, oh wait a second, but it seems like they do something here. It's just a sum of two probabilities. Matches our intuition, tells the probability should be. Similarly, the state can be written as this and this. I don't know, whatever. Two qubit operations. As in a single qubit case, any unitary transformation is a valid operation on qubits. In general, the unitary transformation, for example, the CNOT control NOT gate is a commonly used 2-qubit gate and is represented by the following unitary matrix. So that's transformation. We can also form 2-qubit gates by applying. So CNOT is control NOT. And basically what it says is one, just do a NOT on a qubit if the control qubit is 1. I mean, that's the concept that I think it's also coming from classical computing, but here it's expressed on how that transformation is mathematically represented. We can also form 2-qubit gates by applying single qubit gates on both qubits. For example, if I apply the gates this and this, it's the same as applying this gate. Yeah. Okay. So that gives you the tool set on how you make the mathematical representation of something for 2 qubits. Man, 50 qubits, that has to be a mess. Blah, 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 transforming this stuff. Building controlled unitaries is an efficient major challenge. The simplest way to implement this requires forming a database of controlled versions of fundamental gates and replacing every fundamental gate in the original unitary version with its controls counterpart. More controlled versions to achieve the same impact. This is often quite useful. So here I think they talk about how can you make controlled versions of other gates. But again, maybe I'm going through that too quickly, but this guide doesn't have a smooth introduction to gates if you don't know what the gates concept is. Good. Many qubit systems. Yeah, so as you can imagine, following the same pattern just scales for more qubits, right? So consider encoding a bit string this, which has basically 3, 6, 7. So in a quantum computer, we can encode this like this. Okay. Quantum gates work in exactly the same way. If we wish to apply the X gate to the first qubit and then perform a CNOT between the second and the third qubits, we may express this transformation like that. Okay. Oh, so you see, the thing is, what the X gate to the first qubit, yeah, so the 1 turned into a 0, and a CNOT between the second and the third. Second and third, which leaves them unchanged because it's a 0. So that's my point, is like intuitively, you don't really need to know all the maths behind, because you can operate at that level. I think there's an easy way to just, the same way you would just by hand write different things, like 1 and 1 is 1, like in terms of the AND operation, 0 and 1 is 0. You can probably intuitively build a way to manipulate bit strings from a quantum perspective without going through all that stuff. Finally, although new gates needed to be added to our gate set, the gates universal gate set of many qubits, because in general we work on into series of 2-qubit rotations. Column vector. Yeah. Okay. So that's it for multiple qubits. The gist of it is there is a mathematical tool set to represent that, and it's helpful to reason about things. But it's a bit overwhelming in terms of how to easily build intuition on top of that. So, because it seems like certain things you do with, it seems to me that the certain things you do with qubits or or states impact the data you encode in weird ways, right? So say in classical computing, I would have something like that, and I know how to manipulate those bits. But from a quantum perspective, that's going to be um, it's going to be a tough one, especially that I can't tell here. Can I tell whether that's entangled or not intuitively? For example, I don't know. Not intuitively without having to having to prove whether I can express that into the tensor product of many qubits. So, yeah, many qubits. So, and that scales. And Dirac notation, what is that? Yeah, okay. So yeah, I'm not going to go through that. It just basically tells there's another way to write stuff. So you don't have to write that all the time. You can just write this and this. And here's a bunch of definitions of other, like what's the plus and what's the minus state. It's just the Hadamard applied on the zero state. We can call it a plus state. And those are just conventions. I'm not going through that because I know those. Just check it out. I think those are basics. But I think, okay, so pretty much I haven't really learned anything new. Um, aside from that, was a helpful perspective, this one here, on the effect of measuring a single qubit in a multi-qubit state. But up down until here, and quantum circuits, like, let's do that later. So up to the concept of qubit, I think that's I haven't learned anything new, and that's pretty good. This guy does a good job by not diving too much into the details, but maybe it's a bit of a steep learning curve for someone who really hasn't been reading about quantum gates and all that stuff. Yeah, cool, perfect.